Good morning, everyone. I'm Sandesh Neupane, and today I will introduce you to the Bootstrap method in statistics. We will explore why it is useful, how it improves traditional methods, and I will also show some Python code and visualization to make it clear. Let's get started. Before we dive into the Bootstrap method, it is important to understand why it became necessary. Traditionally, we relied on methods that required us to make assumptions about our data, like assuming it follows a normal distribution or that observations are independent. But what if these assumptions are not met? Or if we have a small sample size? In those cases, traditional method often falls short, leading to less accurate result and more uncertainty. To make this clearer, I have prepared a handwritten solution to walk through our real-world example. This will show the challenges we faced before the Bootstrap method was developed and why we needed a more flexible approach. Let's take a look at height of our 10 students. First, we calculated the mean height, which is 173.5 cm. Now, to find the confidence interval, we need the standard deviation, which is approximately 15.87 cm. Using a t-value of 2.262 for our sample size of 10, we find our margin of error to be about 11.36 cm. This gives us a confidence interval of approximately 162.14 cm to 184.86 cm. This means we can be 95% confident that the true mean height of all students fall within this range. However, notice the outlier at 200 cm. This extreme value can distort our mean and confidence interval, making them less reliable. In fact, the confidence interval only reflects the data we have, which does not accurately represent the majority of students. This limitation is why we turn to the Bootstrap method for more silent approach to estimating our data's true characteristic. So, what is Bootstrap? The Bootstrap method is a resampling technique that helps us estimate the sample distribution of a statistic. Its primary purpose is to provide more reliable estimates of population parameters, allowing us to overcome the limitation of traditional methods. With Bootstrap, we can generate multiple samples from our original dataset, which helps improves the accuracy of our estimates. So how Bootstrap works? For this, we will directly dive into the particular example. As we all know, Bootstrap is a powerful statistical method used to estimate the variability of a sample. In this example, we begin with a school population of 1000 students and take the sample of 30 students. From this sample, we generate several Bootstrap samples by randomly selecting students with replacement, meaning some student may appear more than once in a sample, while other may not appear at all. It's important to note that the sample size of each Bootstrap sample is equal to original sample size, which is 30 in this case. For each Bootstrap sample, we measure the height of the student and calculate the mean height. This process is repeated many times, and as a result, we generate a distribution of mean height. This distribution helps us understand the variability or uncertainty in our estimate of the population's mean height. In our analysis, we generated a set of 1000 samples from a normal distribution with a mean of 50 and a standard deviation of 10 using NumPy. This was done with a simple line of code, which allowed us to create a data frame for easy handling of the data. We calculated the mean of our original data, which was approximately 50.19 and the standard deviation around 9.79. This resulted in a normal confidence interval of 49.59 to 50.80, suggesting where we can expect the true mean to lie. Next, we employed the Bootstrap method, a valuable technique that allows us to access the variability of our data by resampling. In this process, we took multiple random samples from our original dataset. The mean from our Bootstrap sample came about to be 50.20 with a Bootstrap confidence interval of 49.61 to 50.85. Now, let's look at the graph. The first histogram displays the distributions of our normal data. It features a dashed red line that marks the mean value, making it clear where the center of our data lies. The green dashed line represents the lower and upper bounds of the normal confidence interval. The second histogram shows the distributions of the bootstrap mean. Here, a dashed red line again indicates the bootstrap mean. The purple dashed line denotes the confidence interval from our bootstrap method, emphasizing its range. This visual element helps clarify how our bootstrap sample behaved compared to the original dataset. So, in conclusion, the bootstrap method is particularly advantageous because it allows us to account for the variability in our data, including any outlier that might exist. This resilience provides a more robust estimations of the confidence interval, which is critical when making inference about the populations from which our sample were drawn. In scenarios where the underlying distribution is uncertain or the sample size is small, the bootstrap method stands out as a powerful tool for reliable statistic analysis. By using both distribution, we not only confirm our finding but also gain insight into the reliability of our estimate, allowing us to approach our analysis with the greater confidence. Thank you.